All right, so today we're going to talk about vector spaces and linear independence. These two topics might seem very disjoint from one another, so we're going to take them one at a time, but we're going to wrap them up at the end. So a vector space, this is just a fancy way of a line or a plane or a hyperplane that goes through the origin. Algebraically, we can represent it in geometric vector form. So we can represent all of these in geometric vector form. But we want to really connect what really makes a vector space a vector space. So a vector space obeys two important conditions. The first thing is if you have an element of your vector space, you have a thing in your vector space, and you add another thing, you get still a thing. And the second condition says that if you take a thing in your vector space, like a vector, and you multiply it by k, where k can be any real number, then in fact, you still get something that's still a thing. So these are the two important conditions. Now this might seem very disjoint from what a line is or these geometric vector forms, but let's go ahead and give some examples, and then we'll come back and I'll convince you that this is in fact the exact properties of what a line, a plane, or a hyperplane really are. All right, so let's do some examples. So the first example would just be Rn. So to check that out, right, if we take a vector in Rn, and we add another vector in Rn, we still get something in Rn. Okay, so that's just saying that vectors add, and they also scale, just like you would predict. If I take k times a vector in Rn, then you still get something in Rn. All right, so that describes a vector space. You can add and scale in it without leaving that space. All right, let's do a slightly non-trivial example. Let's do vectors in R3 with a 0 in the top component. Right? So this might seem weird. Now, we're not describing all of R3. We're describing a very particular subset of R3, things that are zeroed out in the first entry. And if we want to check, we can check, okay, is it the case that if I take two generic vectors that are zeroed out in the first entry, do you get something that's still zeroed out in the first entry? And sure enough, you do. And if I take a generic form of this vector and I multiply it by k, do you still get something that fits roughly the same form? And sure enough, you get zeros both times. So this shows us that it meets both of these two conditions, and that this subset of R3 with a 0 in the x entry is also a vector space. All right. Another example is vectors in R3 with the same entry. So they look something like AAA. And sure enough, we can go through the properties again. And we can say, okay, if I take a generic form of the vector and add it to another one, then you get something of the same type. And if I take k, some arbitrary real number and multiply it by our generic form, you still get something that fits our form. You have something that's all the same. So this checks out. So this says that this is also an example of a vector space. Now, one thing I should point out is that what's really nice is we can write the vectors of this form, or anything of this form, AAA, is really just the vector 1, 1, 1 times A, where A is some arbitrary constant. So this is just a line. This is a line in R3 in the direction of 1, 1, 1. So this is kind of what this vector space looks like. It's going to take a vector and it's going to trace out that line in this particular case. Right, so it might look something like that. And so the goal is to take all of these vector spaces and be able to describe them in a very nice, concise way. So in fact, if we go up to this previous example here, where there's a 0 up there, we can write everything of that form. We can write it as something that looks like this. Right, so if you want something that's not 0 in the, that is 0 in the X entry, you can write it as something time, the Y entry plus something in the Z entry. And more precisely, you can write it like this. And what does this look like in R3? This means we take certain vectors. We'll take the 0, 1, 0 vector and the 0, 0, 1 vector. And now this isn't going to create a line, but it's going to create the grid generated by all of these vectors. So this is going to create a grid that's going to turn out to be a plane in 3 dimensions. So in this particular case, you're going to get the grid that is the YZ plane in R3. And the key is we were able to describe it with exactly these 2 vectors. So let's go on to the last example that I think is very important. Any span of vectors is a vector space. So keep in mind that span here means any combination. I can take A1, V1 plus A2, V2, and so on. That if I have any vectors, then any combination of them, any sum of multiples of them is going to be in the span. So algebraically, anything in the grid of vectors looks like this. It's in the span. And this creates a vector space. So let's check property 1. If I take 2 vectors of this form, right, so I take a generic form of any linear combination of these vectors, and I add it to something of the same type. So here I'm using B because the B's aren't necessarily the same as the A's. They're just indicating that there's some different combination. It could be the same, but it's probably not. And I add them together. What do we get? Well, we get a combination of the vectors where instead of A or B, I'm going to move A plus B steps in the V1 direction and A2 plus B2 steps in the V2 direction, and AM plus BM steps in the VM direction. That new vector is still a combination of our original vectors V1, V2 through VM. And likewise, to check the second condition, if I take some combination of vectors and I multiply this all by K, where K is some real number, well, this is just the same thing as KA1 times V1 plus KA2 times V2. And instead of taking A steps in the V1 direction, you now take K times A1 steps in the V1 direction and K times A2 steps in the V2 direction, and so on. And this is still something where there's something times V1 plus something times V2 plus something times V3. And it's just that something has slightly changed depending on how we've modified it. But if you scale a vector, you're still in that grid of vectors. Okay. So far we've come up with some examples of vector spaces. And one of the goals that we want to be able to do in the long term is describe vector spaces concisely and precisely. And so this is what's going to give us the concept of linear independence. And the main question we want to ask is, do we have too many vectors? So for example, I might consider the span. That just means the grid generated by these three vectors. So what does this span look like? Well, this span's going to look like 1, 0. And then we're going to add 0, 1. But now we can take combinations of any of these. And you can see already, we can already get any point in the plane. The grid that we're building here already generates all of R2. Right. And since we can use combinations of these, it's going to form this nice grid. I can get to any point I want on this plane. But the span also needs grid lines for 1, 1. We said that 1, 1. So 1, 1 is going to look like this. And we're going to add this second grid. But now you might be saying, okay, wait. This is two-dimensional space. This is R2. And we have 3 vectors. Why do we need 3 vectors? Well, we don't need 3 vectors. That's the point we're trying to make. But the main question is, how can you be so sure we don't actually need all 3 of these vectors to describe all the points in R2? Well, it turns out that we can take 1, 1, and we can write this as some combination of the other 2. Right, we can write 1, 1. Right, this vector 1, 1 right here is simply a combination of 1 step in the 1, 0 direction plus 1 step in the 0, 1 direction. So adding the purple vector, adding the 1, 1 vector to our grid doesn't do anything because we can already get there. It just makes it look messier and more ugly. So this brings us about the concept of linear independence, right? Your span is nicely described if all of those vectors are going to be linearly independent. And you're linearly independent if no vector can be written as a combination of the others. Right. So we want to be able to say that no vector can be written as a combination of the others. And there's another way of thinking about this. Or if you take a bunch of vectors you take a bunch of vectors, the only way to get to 0 has only the solution A1 equals A2 equals AM, which is equal to 0. So the other way to say this is that this equation right here has only the 0 solution to do it. This says the only way to get 0, if your vectors are truly independent, the only way to get to 0 is to never move at all. Right? So if you think about here, right, we can actually create the 0. We can actually not move at all. If we start here at the 0 vector, we could move in the 1, 0 direction, move in the 0, 1 direction, and then move backwards in the 1, 1 direction, and we'll get back to where we started. And we're using different combination that's just not all 0. That's one indicator that, in fact, they're all linearly dependent with one another. One good way of thinking about linear independence, so geometrically, this means they are all essentially in different directions. Right. So it's kind of hard to say what does it mean to be essentially in different directions, because they all point in different directions, but the essential thing means that you can't, that they're in a new dimension. So here we have the 1, 1 is essentially in the same direction as both 0, 1 and 1, 0. It's a little bit of an intuitive idea, but the idea is that you're going to be linearly independent if you're all in essentially different directions forming different dimensions. So let's just do kind of a hands-on example here. So right now we want to ask, are certain vectors linearly independent? So we might take certain vectors. So let's consider the vectors, are these vectors 1, 2, 3, 2, minus 1, minus 1, and 4, 3, 5 linearly independent? Right. And if you look at them, it might be easy to say, look, those are all different directions. They all have different numbers. They're not scalar multiples of each other. Clearly, they must be independent. But maybe, just maybe, they're actually going to be combinations of one another. And we want a robust way of figuring that out. So going back to this idea right here, instead of trying to write one as a combination of the others, we're going to try to look at this way of thinking. We're going to ask, is there a way to get 0 among them? Is there a way to combine them together? To get the 0 vector in a non-trivial way. So this is the same thing as asking, is there a non-zero solution to this? Or maybe more accurately, is the only solution 0? If they're linearly independent, then in fact, it will be the case that the only solution is the 0th solution. Okay, so how do we do that? Well, keep in mind that this array of vectors is the same thing as multiplying xyz by this matrix, this vector, xyz by this matrix. And we all know how to solve this. We want to check, does this have a non-zero solution to it? So we can write this as an augmented matrix and then go nuts. So we're just checking. All right, so we're going to solve this matrix, but keep in mind, our goal is there a non-zero solution? That's our goal. That's why we're doing this. All right, so we're going to go check this out. So we have our pivot, but we're missing this guy right here as well as this one. So we're going to do R2 minus 2R1 and R3 minus 3R1. And when we do that, we're going to get 1, 0, 0, 2, 4, minus 5, minus 5, minus 7, minus 7, and 0 is all on the right. All right. So now we're going to move on to this gun. Divide that one by minus 5. And now we're just solving the solution. We need to get rid of those guys to make this an echelon form. So we're going to do R1 minus 2 row 2 and R1 plus 7 row 2. That's row 3. And so what's going to happen here is we're going to end up with 1, 0, 2 and 0, 0, 1, 1. Okay. So now we have this in echelon form. And from here, we can kind of indicate that we have two pivots, which means we solidify two dimensions, but there's going to be one free variable, which means we have some freedom to pick the solution to this. So let's figure out what that is. Now, at this point, you could probably guess that it's going to not be linearly independent because our question was, is there a non-zero solution? Well, there is. The answer is yes. The answer to our question is yes. So that means that it's going to be linearly dependent. They're not in free directions from one another. But let's figure out exactly what the relation is. So this first equation means x plus 2z is equal to 0. And the second equation corresponds to y plus z is equal to 0. So if we put this in geometric form, right, we're going to solve for x and solve for y. So we get that x is minus 2z, y is minus z, and z is free. So it just becomes z. Or more accurately, we can factor out the z. So now we get a line. All right, so it's kind of weird what this thing actually means right here. What does this line mean? Well, this just means this gives us the solution to our original equation. So we can pick, the z is free, so we can pick whatever we want for z. So let's try z equals 1. Now at this point, we should be convinced that they're linearly dependent, but let's actually explicitly demonstrate why they're linearly dependent. So we're going to try z equals 1. And if we try z equals 1, that means x, y, z has to equal minus 2, minus 1, and 1. So that means that 1, 2, 3 times minus 2 plus 2 minus 1 minus 1 times minus 1 plus 4, 3, 5 times 1 better be equal to the all zero vector. And sure enough, that pans out, but let's just be more explicit. Let's solve for that vector, the 4, 3, 5 vector. So we're going to put all the others on the other side. And when we do that, we get that 4, 3, 5 is equal to minus 2 times 1, 2, 3 plus 1 times 2 minus 1 minus 1. And now it's evident that because we can write 4, 3, 5 as a combination of these other two, that it is not essentially a new direction and therefore it's linearly dependent.